Oh my goodness, there you all are. Hey, how's it going? Well, thank you for showing up for your learning. We are going to continue with angles in standard position, and we're going to determine an angle given a point. Okay. One thing that we're going to notice as we investigate these angles that are obtuse or reflex, meaning they're bigger than 90 degrees, is that we're no longer going to have a clear opposite and adjacent. We're going to have to expand our thinking outside of triangles and think a little bit more about x and y points. Okay, so let's take a look at this example. P is the point that we're interested in. P is, I'm going to do this in delightful purple here, is at -6. I should have this marked. 1, 2, 3, 4, 5, 6. And then 1, 2, 3, 4, 5. That's the point, -6, 5. Correct me if I'm wrong. I sometimes do this. -6, 5. Okay. If that was over here at 6, 5 over there, like JP might be 6'5" when he's done growing. Who knows? Over here, maybe Fisher is more likely to get that tall. Certainly not me. Over here, we would have a very clear opposite and adjacent to this angle here. I'm going to call it beta because we're going to find it is the reflex angle for this one over here. Okay, this one would be 5 high, and that would be 6 high. This would be the point 6, 5, and the radius there is not the radius, but the hypotenuse. Let's go ahead and find the hypotenuse because it's going to be the same over here or here. We would say the hypotenuse squared is equal to, yes, square root of 61. We did this yesterday, right? Yeah. So for those that didn't see this yesterday, we would do 6 squared or -6 squared. Doesn't make a difference. It's the same number. Plus 5 squared gives us 61. And then in order to find h, you take the square root of both sides. It's the square root of 61. Cool. All right. So now if we were looking at beta, okay, let's take a look at beta here. We would say sine beta is equal to, well, we know the hypotenuse is the square root of 61, and it's the opposite side over there, so that's 5. Notice that that is the y coordinate of my point over the hypotenuse. It's the y coordinate there. Cosine beta would be equal to 6 over the square root of 61, and that's the x coordinate over the hypotenuse. See, this x came up here. And then what if we were looking at tan beta? Well, tan beta would be opposite over adjacent. That's 5 over 6. And that's the y coordinate over the x coordinate. These are kind of the things that we're going to expand as we look on the other side. So let's shift to forest green for the pure delight of our eyes. And we're going to take a look at this angle here and try and calculate that angle. This is the angle we're interested in. That's theta. And if we look at the different things for theta, well, sine theta is going to be equal to, okay, we're going to look for the y value there and put it over the hypotenuse. The y value is 5. So we would have 5 over 61, but it's the square root of that. Okay. So now what you can kind of do is drop this down like a shadow and take a look here. This is 5. So that's still kind of opposite this angle. And this one over here, this is, well, -6 there. And that would give us cosine of this angle. And if you think about this as the adjacent side to that angle, well, I suppose you could. But I would think of it more as the x value of that coordinate point. So that would be -6 over square root of 61. Notice that the trigonometric ratios were the same for sine, but just the sign was flipped on cosine. If we take a look at tangent of theta, it would be y over x. So that would be equal to 5 over -6. And that is the same thing as tangent beta, but the sign is flipped. Now, why are we having the same values, but the signs are flipping? Well, let's see. Cast rule. Cosine is going to be positive down there. All of them are positive over here. and no wonder all of these were positive for beta. Over here, only sine is positive. Why is that? Because only the y values are positive over here. The x values are negative. And then down here, tangent would be positive in the third quadrant because both sine and cosine are negative. Are you laughing at the baby noises outside the hall? Yeah? Okay. Cool. I think it's perplexing as well. All right. So that's how you find the sine, cosine, and tangent of these things. And yesterday, I can recall we used one of the inverse functions to find this angle. Let's use a different inverse function. Let's use tan theta and see what we get. So let's take tan inverse of 5 over negative 6, and that should give us theta. Let's see what we get. Calculator, turn it on, move it over here, see the calculations. We're going to calculate this one here. So I'm going to take 5, divide it by 6, but it's negative, and that equals negative 8.3 repeating. I go into trigonometry, and I take the inverse tangent of that. Oh, and it tells me negative 40 degrees. Oh, yeah, that's what we had yesterday. Darn. Okay, darn. All right, so anyway, it tells us theta is equal to negative 40 degrees. Oh, darn.
Can we ignore the negative? Or can we just ignore the negative?
No, we're not going to really ignore the negative. But what we're going to realize is if we take a look at, I'm going to draw negative 40 degrees, but in blue to delight the eye. Over here, like that, it's going to look like this. And it's actually going to be, notice if I drop this down here to there, this would be the point 6, negative 5. Right down here. And if I did the tangent for that, that would be negative 5 over 6 is the same thing as 5 over negative 6. Right? The tangent for that angle, this angle here, we'll call it Q. Okay? Angle Q equals negative 40 degrees. Our calculator just told us. And that would be to the point 6, negative 5. Tan Q is equal to negative 5 over 6. And for those that know, negative 5 over 6 is exactly the same thing as 5 over negative 6. Your calculator doesn't tell the difference between those two things. So it likes to give you this answer instead of this answer, which we actually desire. So what do we do? How do we find it? Well, we know that they share the same reference angle. So this one over here has the same reference angle, beta, as this one. So this here is negative 40 degrees. So I would do 180 minus 40 degrees to get 140.
Yeah. So you just leave it at the 40, the negative.
Yeah, I'm going to do 180 kind of plus that. You know what I mean?
Yeah.
If I knew that the angle was in the third quadrant, I'd do 180 plus 40. Or minus 40. Right?
If it's in the fourth,
Plus 40.
you use 360. Oh, no,
Yeah, and if it's in the fourth quadrant, you do 360 minus that.
Yeah.
Like even here, if I want to know Q, but as a positive angle, I'm going to do 360 minus 40 to get 320.
Yeah.
320, the same thing. It's just around there
Yeah.
instead of going the short way. Okay, so let's try cosine and see what our calculator says if we try cosine here. Because here's why I'm predicting that it will actually give us the value 140. Because cosine is going to be negative over here and over here. And it's not going to prefer to give us this angle that will go down to this point. It's going to prefer to give us the shorter one. So let's try that. Okay. And this would be a way you can kind of check your work and confirm. So I'm going to do here negative 6. So this is 6, but it's negative. Divided by 61, but I take the square root of that. Equals. Here's the cosine. Let's do the inverse cosine of that. There it is. So there we got it. We kind of bullied our calculator into cooperating. Okay. So if you can overpower your calculator with your sheer persistence, you can sometimes get your calculator to output the angle you're looking for without having to do any tricks. However, if your angle is in the third quadrant, good luck. It's always going to output something in the first, second, or fourth, I believe. Most calculators will do that. It's just a calculator choice. Okay. Now this is what I encourage you to visualize is the unit circle. See the unit circle, see that arm moving, and imagine what other angle would have the same sine, or what other angle would have the same cosine. Okay? And there's always going to be one and exactly one other angle that will have the same thing because of cast rule. They're both going to be positive in 2 quadrants and negative in 2 quadrants. Let's keep going. Let's look at the next example. Let's say we have an angle in standard position and sine x is equal to 4/5.
We write this down.
Sure.
Wait, like here.
Maybe you can make a little sketch or something, or just watch me work through it. Yeah.
I don't know if it's up there.
Cool. No, don't worry about it. We'll come back to that another day. But it's in quadrant 2. Determine the other 2 primary trigonometric ratios. So I want to find cosine of x and tan of x. Now, how am I going to do that? Well, first of all, I want to know around where this thing is. The 4/5, I can think of that. This is sine, so it's like y over hypotenuse. Huh?
How do y and x get incorporated with sine and opposite and hypotenuse?
Let's change this example. I don't like that they did sine x. Let's do sine theta. Okay? We're going to do sine theta because we're comfortable with theta as angles. So let's do that. That's sine x. You can label your angles letters if you want, but not here where we're talking about xy plane. Okay, so we're changing the example to make this clearer. Okay, 4/5 is sine. So sine is y over h. Well, I know this because sine tends to correspond with the y values over the hypotenuse. Okay, so over here, when we looked at beta, I'm just going to zoom in on beta so that we can really see. Beta here, its opposite is 5, and that has to do with its y values. Its adjacent has to do with its x values of this point here. So now I'm encouraging you to think a little less about opposite and adjacent and more about what's the x value of the end point of the terminal arm, what's the y value of the x point of the terminal arm.
Mostly y values.
Sorry?
Hypotenuse is mostly situated about y values.
Sine is associated with y values over hypotenuse. Cosine is x value over hypotenuse. And tangent doesn't use hypotenuse. Tangent just uses y over x. Okay, let's keep looking here. So what I know is that this is some angle that has its terminal arm touching this line y equals 4. And I notice that regardless of how long it is, there could be 2 of them. It's a line that's 5 long, so I need to know what would the x value be to create a hypotenuse 5 long. So let's draw my hypothetical triangle. Let's say I don't know the answer, and I say, well, it's going to be something like this. This is going to be 4 high. This is going to be 5 long, and I don't know this x value yet. Let's call it x. I do know it, but let's say I don't. Okay, so what I would do is set up my a squared plus b squared equals c squared. And I have to make sure I put the hypotenuse as c squared. So that's going to be 5 squared is equal to, well, one of them, 4 squared plus x squared. 4 squared is 16. 5 squared is 25. So I'm going to subtract 16 from both sides. And I get x squared equals 25 minus 16, which is 9. Therefore, x is equal to 3. I've just solved for where that point could be. But there is another. Negative 3 could also work. Negative 3 squared is also 9. So it's actually plus or minus 3. So here are the possibilities for where my x is. It's not over here where I drew it, okay? Because this would be 3, but I was told it's in quadrant 2. So let's use negative 3 for x, positive 4 for y. Here is the end point of my terminal arm, and now I have a good visualization of this angle here, theta. Okay, that's my angle theta that I'm measuring. I notice that really looks like it's bigger than 90 degrees. Always start with a guess. And I also predict it's a little less than 135 because 135 would be like a 45-degree angle going up this way, and it's not quite that. It's not quite a 45-degree angle. So we can label this point as negative 3, 4. And we can write the other ratios. Cosine for this would be -3 over 5, and tangent would be y over x, so 4 over -3. Okay, so now we have found the other two primary trigonometric ratios, and the question didn't ask for it, but let's find theta for fun. If I use sine, 4 over 5, aka 0.8, so I can do here, clear that, type in 0.8, which is 4 over 5, take the inverse sine of that, and get a little frustrated that it gave me an angle in the first quadrant. If I want to find out what that angle would be in the second quadrant, I would do 180 degrees minus that. Why would I do 180 degrees minus that? Because it looks like this. I would go 180 degrees minus that reference angle to get there. And 180 minus 53, well, that fits my prediction. It's about 127. It's a little less than 135. Cool. But I bet if we use cosine, it's going to give us exactly the angle without us having to do some rigmarole. Because cosine is negative over here and over here, and it's probably not going to give me the answer in the third quadrant. So let's check my calculator and see. Oh, this is going to be so good. 0.6, but it's negative. That's 3 over 5, but it's negative. Take the inverse cosine of that. 126.8. That's 127 degrees. There it is. So we bullied our calculator into telling us, but you can't always bully your calculator into telling you. You need to have these visualizations of these arms going around in circles and saying, well, I know which quadrants it's in. I know which trigonometric ratios are positive and negative there. And I can use my reference angles to figure out the actual value by either adding it to 180 or subtracting it from 180 or even subtracting it from 360. Cool. So now what you're going to do? Well, you're going to learn about coterminal angles. Just a quick idea here. If I told you that I had a 120 degree angle and you said, nah, you've got a negative 240 degree angle. And then we had a big fight about it. And Fisher was called in to adjudicate the fight. Fisher, who would you say is right? Yeah, they're both right, but if you're fighting, you're probably wrong. I agree. Yeah. 120 degrees is the same thing as negative 240 degrees. These are what are called coterminal angles. But what if Isaac came along and he said, nah, all of you are wrong. I spun around twice in a circle and then checked, and it was 840 degrees. Ooh. Then who's right? All of us are right. Why is 840? Oh, you're just right, because that makes you feel better. Yeah, okay, all right. We'll let Isaac be right. We all agree to let him win this argument. But we all need to be in agreement that 840 degrees is just, I go around in a circle once, that's 360, twice, that's 720, and then I add 120 degrees on there, that's 840 degrees. It's just the same thing as 120. It's like saying, when will the sun be right there in the sky? And you could say, well, it'll be right there in the sky in an hour, or in 25 hours, or in 49 hours. You're correct either way, because the sun's going to be there every 24 hours plus 1. The circle's going to turn and turn and turn. So we're going to see a lot of these things where the wave goes up and the wave comes down, and you say, when are we at the top of the wave? Multiple answers possible. Okay, so that's the idea of coterminal angles. Find me 3 more coterminal angles that are identical to 30 degrees. Tell me.
Wait, how do you do it?
So 30 degrees. I heard -3, 30 degrees. That's good.
What if you would go from the y coordinate to do 90, and then
Some more answers that people have?
120.
120, no. 120 is different. So have your visualization going as well. You first visualize 30 degrees. And then if you visualize 120, 120 is up there. 120 is up there. That ain't the same thing.
Yeah, so sorry, 180, and then
We want exactly the same as 30 degrees, not like having some trigonometric ratios that are the same. 1070?
I said that earlier too. 990.
He says as with a question mark face. How about
What about
3,630? How many times do I go around in a circle? 10 times. Yeah, I just did 10 times 360, and then I move a little bit more. 1,470. 240? No, 240 is different because we haven't gone all the way around a circle yet. 240 would be down here, like that. That's 240. That's 90, 180, 180 plus another 60. It's quite different.
Sorry, I was just going from the Y.
You better be sorry.
Ah.
Jeez. All that time we spent together and you don't know this instantly. How dare you? So, yeah, that was a little harsh. You don't need to know this the first time I show it to you. That's fine. I'm just joking around. You want to just think about like there are the negative options, and Avery had that right away. That would be negative 360. Sorry, negative 330 is the same thing as 30 degrees. And then we can also do like another minus 360 here to get to negative 690 degrees. Okay, would also be another option. Then you could subtract another 360 to find another one. And that would be negative 1,050. Right? Negative 1,050? I think so. So now let's check. Here is, if I'm just going to clear everything. Here's 30 degrees, and I take the sine of it. Oh, isn't that interesting? Sine 30 is 1/2. Cool. I bet that's going to show up in tomorrow's lesson. All right, let's try, instead of that, 1050, but it's negative, and I take the sine of it. Oh, it's also 1/2, because it's the same angle.
It's like magic.
Super magic, yeah. Different inputs, the same output. Is that a function? Yeah, but you don't sound really sure. Because I'm asking a trick question again.
How do you know that?
Oh, man. Well, because you just want a unique output for every input. The outputs have to be unique to the inputs. If I input sine 30 and could get a multiple different answers, then that would not be a function. But just the fact that I can input different things and output the same thing, yeah. And so let's just take a quick Desmos peek here. A quick Desmos peek at something sinusoidal. Boop, 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 boop. Sine of x, boom, there we go. And notice that I can get like the same output of 1/2 here. And then over here, this is 1/2. Let's just graph the line y equals 0.5. And what we have here, oh, and then I'll actually change it to radians, from radians to degrees, and show you x values up until 1,440. Oh, there we go. Okay, so here's the degrees, and here's sine, and I'm going to zoom in a little bit on the y, because why not? 2 and negative 2. There we go. So now we've got a really good look at this sine wave curve that we're going to study next unit, and I wish we'd already studied because it's really useful for understanding all these topics. All right, there is 30 degrees. That's our first intersection with 1/2. This is the same angle, but in the second quadrant, because sine is positive in the second quadrant. That over there, if I check that point, it's going to have the same reference angle. That's going to be 150. Let's check. Boop, 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 150. And then our next intersection is at 390. That's 360 plus 30. And then these, note that 150 is not the same angle as 30 degrees. It just has the same reference angle. But 390 is absolutely the same thing as 30 degrees. We've gone around the circle once. Okay? When you're rising, you're going like through the first quadrant. When it's descending, it's going through the second quadrant. So this is like the second quadrant the second time after we've gone around the circle once. This would be 720 plus 30, that's 750. That would be plus another 360, so that's going to be 1,110. See, that's 1,100 there, that's 1,110. And then this is coming down the second quadrant again. Okay? So that's showing you as you rotate that circle, you're going up and then you're coming down, then you're going up and then you're coming down for your sine values. Or the y value of the end of the arm is going up, and then the y value starts coming down until the y value becomes negative, and then the y value becomes positive, and then oh, the teacher went in a loop and forgot to show us the homework problems. Oh my goodness. No, I'm not in a loop. There you go. This is what we'll practice. I'm coming around my traveling math show to visit a table near you so that we can do some of these problems together. Questions before we start?
May I use your text message?
Yeah. Bye for now, everyone. Thanks for showing up for your learning. Team Learn at Home.